Hello there. In this video, I want to continue to talk about what I've been talking about so far in regards to like terms. And I want to talk about that in the context of simplifying radical expressions, and specifically adding and subtracting radicals. It's important that we talk about this because I've always liked to look at the idea that a radical is kind of like a variable. We can represent that with variables. So, for example, this first one, square root of 2 plus square root of 3, this is not equal to the square root of 5, okay? And if I wanted to demonstrate that, I could demonstrate that by relating it back to what we know about algebraic notation. Say, let's x equals square root of 2, and since I can't use x again, I would have to use something else for the square root of 3. Let's go with y. And already we can start to see this form. So if I substituted this, this would just be x plus y. And from simplifying like terms with variables, I know that there's nothing I can do about this. I talked about x and y being lengths in the combining like terms video, but they would be different lengths. And we can see that represented by the fact that x equals a length of square root of 2 and y equals a length of square root of 3. So this is already simplified. Already simplified. Okay. What about this next example? Now, it's not completely simplified. There's something we can do. We've got 7 times the quantity square root of 3 plus the square root of 4. So this would simply be 7 square root of 3. Square root of 4 is 2. So we get a little simplification out of it. But in terms of combining these terms together, there's nothing I can do. And we could do the same proof with the representations of letting x and y, or different variables, be 7 square root of 3 plus 2. We would have to let them be different variables. And we would have to just deal with the fact that there's nothing we can do to combine them. But what about this next expression? Let's try the same thing. If I let x equal the square root of 5, well, right off the bat, I can say that then this is, if I take out this first square root of 5, that's x. And if I take out this second square root of 5, that would equal 2x. And I know there's something I can do here. Again, pretend that's 1, or know that it's 1. Don't pretend it is 1. And then we do 1 plus 2, that's 3x, and therefore my answer is actually 3 square root of 5. Now, do you need to do this kind of substitution every time you simplify these? No, just treat it like it's a variable in your mind. I have 1 times the square root of 5 plus 2 times the square root of 5, and I add their coefficients together. 1 plus 2 gives me 3. So let's talk about a few more complicated examples. Square root of 54, now we're talking in terms of subtraction. Square root of 54 minus square root of 24. Well, on the surface, it seems like there's nothing we can do about this. I mean, they're not like terms. There's nothing we can do about it. However, the numbers on the previous page were simplified radicals. So we're talking about square root of 5, square root of 2, square root of 3. Those were all prime numbers, so there's nothing we can do to simplify it. However, 54 and 24, we can simplify those. So let's go our simplifying radicals process first. So I'll set up factor trees for 54 and 24. 54 is 9 and 6, 9 is 3 and 3, and 6 is 3 and 2. And then 24 is 4 and 6, 4 is 2 and 2, and 6 is 3 and 2. Okay, so I got a pair here, and then I've got lone numbers here and here. So square root of 54 would be equal to 3, and then 3 times 2 has to get put back in the radical, so that'd be 6, square root of 6, pardon me, minus, and then we can come over here, we have a pair of 2, so that'd be a 2 outside the radical, but then we've got 3 and 2 by itself, and it turns out we actually do get a common term here in the square root of 6, so we can treat this as 3 minus 2, which would be 1 times square root of 6, or we could just write our answer as the square root of 6. Let's talk about one more example. We got the square root of 81 minus the square root of 243. So square root of 81, I'm not going to do a factor tree for that. Let's go ahead and just call that 9 now. Square root of 243, I will do a factor tree for that. So 243, I know that to be 3 and 81. But then I know 81 is 9 and 9. And I'm actually going to stop my factor tree there to demonstrate that when you come to this, and I explain this in my Simplifying Radicals video, you can just take that as your pair and not have to worry about anything else. And then we got the remaining 3. It's personal preference, though. So this is minus 9 square root of 3. So long as you do the math correctly, you should get 9 square root of 3. Okay. Now, on the surface, this looks simplified. If you wanted to simplify it a little bit further, we do have a 9 we could factor out. So 9, and then if I divide 9 out of 9, because that's what factoring is, division. So 9 divided by 9, that just gives me 1. And then if I take 9 away from all this, I'm just left with 1 square root of 3, or just square root of 3. And either answer are fine. It is personal preference which one you determine is the best option. So go ahead and hit that like and subscribe button. And if you have any ideas for additional videos in the future, please leave them in the comment section below. Thanks for watching.